All right, hey everyone, welcome to the next in our installment of a series of lightning talks about wildfire and wildfire management technology. Today, I have the pleasure of welcoming David Robinson. David joins us as a postdoctoral researcher from Los Alamos National Lab, where he studies complex fire modeling techniques. He has a doctorate in computational science from Florida State University, where he was the very first graduate of the department's fire dynamics doctoral program. Who better to talk to us about all of the inputs that go into fire models, and especially why it's important to have vegetation models and tree lists that are as accurate as possible. Welcome, David. Thank you for taking the time.
Thank you, John.
Well, David has some slides for us, so I'm going to back myself out of the frame here, and he can share his screen. And then when we come back, maybe we'll have a couple of questions.
Okay, awesome. All right. Well, yeah, so I'm going to give a brief overview on kind of the dynamics that go into how a fire behaves, essentially the three things a fire needs to sustain itself, and then how fuels can affect that fire behavior. So getting right into it. Here I'm showing what's called the fire triangle. This is something you'll see pop up all over the place in terms of when you're looking at people discussing wildland fire. But essentially, it's kind of the three components that are considered to be required to sustain a fire. And so you can see we have heat, fuel, and oxygen. So just getting right into it, first off, heat. So this is the heat that is needed to sustain the reaction that is fire. So, you can think about you may need a match to light a fire, but you don't necessarily need to sit there and hold that match once your fire is lit. Reason being, the heat released from that fire is being fed back into the fuels, and that's what's actually sustaining the fire is the combination of the heat from that combustion going into the fuel and generating more combustibles. The way those combustibles are generated is from a process called pyrolysis. And so when you have this organic material and you apply heat to it up to a certain point, the material starts to break down and then produces a gaseous mixture of a whole bunch of components. And when that mixture gets mixed with oxygen and gets heated up to a certain point, that's when you get a flaming reaction. And so, really, what you see when you're looking at a flame is a mixture of all these different particulates and gases with oxygen at a high enough heat that's producing a flame. Um, so, given that, if we go into kind of each one of these legs a little bit, first off, we have oxygen. And so, one of the kind of things that most people probably already know is when your fire's dying down, you can go up and blow on it. And if you blow enough, you can get the flames to reignite in that. Well, that's because, well, one, you're heating up those embers to a high enough point that you're getting enough pyrolysis to generate the gases. But then also, once you get that flaming mixture going, introducing more oxygen through your breath is actually increasing the intensity of that flame. And so this is kind of the thing that most people know with strong winds, you can get more intense fire and you can also get faster spreading fires because of that. Because not only is the wind blowing that heat around, but it's also creating stronger burning fires. So they can burn more or less flammable fuels, we'll say. Um, so then next leg of that, we have heat. So like I was saying earlier, there, some fires require some heat to start the reaction, but you don't have to just sit there with a lighter the whole time, or else campfires really wouldn't be a thing. But the other important thing to kind of note there is that the heat of a fire isn't just within that flame, like we know with a candle. You don't have to stick your hand in the flame to burn yourself. All you have to do is stick your hand up above it. And so what's really going on there is that heat, the energy released from that flame is actually heating up the air up above it. It's also radiating in terms of light. But if you stick your hand up there, you get burned not directly from the flame, but from the transport of that energy through the air into your hand. And so that's one component. But the other thing to think about with that is with a fire, as it's heating up the air, it's creating this buoyant air column that's rising up. And so what that ends up doing is because all that air is going up, it starts creating convective currents because of the heat in the air, but it also draws in surrounding air because the fire's heating air up above it. That air rises up, and then surrounding air is pulled in to fill in that empty space. And so a fire, in a way, ends up feeding itself with its own wind because of the buoyant rise that's generated from the hot gas created from the fire. Um, and kind of the last leg of that is the fuel. And so I like to think of fuel as coming in two flavors, and I speak about them in terms of like their thermal properties. So kind of the first one is thermally thin, and then we have thermally thick. So thermally thin fuels aren't, you don't really need to treat them as the solid block of material. They have material properties, but they're thin enough to where if you heat them up, you're essentially heating up the whole element. And so these are things like grasses, leaves, needle litter, and this can be either on the surface or on the trees themselves or on bushes as well. And these are your typical carriers of fire. When you think about a fire spreading across a landscape, it's these thin fuels that are really transporting the fire at the rates that you typically associate with them. Um, but the other side of that equation are these thermally thick fuels. So these are your logs, your sticks, and shrubs kind of live in both worlds because shrubs have a lot of thin material on them, but they also have very woody parts. And you'll see this referred to as typically like coarse woody debris in terms of what's laying on the surface. What makes these different is they take a bit more energy to get the flaming reaction to get going, but they also are temporally last a lot longer. And so this can have significant effects in terms of if you get a log ignited in a fire, it exposes the soil to a long duration of energy. But also, if there's a canopy up above it, then the canopy then becomes exposed to that buoyant hot air that's rising, or it possibly even directly flames. So there can be significant effects in terms of pre-mortality, depending on where these thick fuels are and if they are ignited. And then even another caveat to that is thick fuels, since they operate on a much larger time scale, they can do a lot more of peculiar things in terms of you can have logs that sit and smolder all night long. Morning comes up, the winds pick up, and with that increase in air and oxygen flow, they can reignite and restart fires after a very long time. And so, and the kind of the more obvious point with fuels is that the heat that's released from these, that energy is coming from the mass within those fuels. So it's very important to be able to say how much mass we have of a certain fuel is a certain somewhere, because that ultimately is going to tell us what the energy budget for that fire really is. And then kind of beyond just those three legs, there's a really important aspect within the fuels, which is the moisture content. And so kind of the main crux of this issue in terms of talking about a fire sustaining itself is really just the fact that liquid water can only come up to its boiling point. It doesn't get any hotter. Once it gets above that, it evaporates, turns to gas. And so ultimately within fuels, if you're going to combust them, you need to remove that water. And so since the pyrolysis doesn't happen until around 500 Kelvin compared to boiling point being around 373 Kelvin. And so the point being here is that you really need to know how much moisture is within a given fuel to know how much energy it's going to take to actually ignite it. But then also there's a bit of a balance that happens here where your ultimate determining whether a fire is going to carry or not ultimately lies on how much energy is within the mass of those fuels, the dry fuel, and how that compares with the amount of moisture content within those fuels. There can be, if you have too much moisture, you can light a fire, but it may eventually self-extinguish because that energy is going into heating up water and evaporating it before it's going into the pyrolysis process to actually sustain a flame. And so that's a really important aspect of describing fuels. Okay, so now going back into those three legs, but from more of a fuels focused context, we can think about how 3D fuel structure affects those three legs. And so first off here, this is kind of talking about the oxygen. And really, I'm kind of thinking about wind in this case, but I have three examples on here. But fuels can act as an obstruction and also an amplifier in a sense to how air gets to a flame. So on the top case, we have a completely open environment. So, wind will feed that fire depending on the wind, is how intense that fire can burn. In the second case, I have a tree just out in the open. And I'm more of thinking of a forest canopy in this case, but what a tree does essentially in terms of how it affects the wind is it actually can channel the wind near to the surface and actually speed up what the background wind actually is because the air has to go around the canopy of that tree and then gets funneled underneath. So you can kind of see the flame tilting away. It's a little bit more intense. Or you can have cases where if you have a fully forested tree with a fully forested forest with shrubs as well, that vegetation can act as an actual barrier to air inflowing to the fire. And so you can see the flames kind of leaning towards this obstruction. And really this relates back to what I was talking about the buoyancy generated by these flames. In the case where there's channeling underneath the canopy, well, it's just driving into the fire and pushing it away and making it more intense. In the case where the wind's obstructed by this canopy, the flame will actually tilt back towards that obstruction because it's trying to pull in air around it, but it's getting restricted from the side where the physical obstruction is. And so it'll actually cause the flame to tend towards that obstruction. So knowing where these physical obstructions are in terms of where a fire is happening and the relative background wind is really important for predicting fire behavior. Okay, so now the heat leg of that in terms of 3D fuels. So again, the vertical structure of these fuels is very important in terms of knowing places where you could run the risk of igniting a canopy fire, let's say. And so, there are definitely cases where you can have a fire on the ground that runs underneath the canopy and is perfectly fine, depending on how much fuel is on that surface and also what the separation is between the surface and that canopy. But you can definitely have cases where if you have much more loading on the ground in terms of fuel, that fire can burn intense enough to actually ignite the canopy and you can develop a canopy fire. And again, it's not necessarily just the flames themselves, but that heat released by those flames that can ignite it. But in probably a more straightforward way of thinking about it, if you have shrubs in the way, these act as what's called ladder fuels. So you can have a surface fire that kind of goes up, ignites some shrubs that gets it that much closer to the canopy. And in a way, the fire climbs up into the canopy and ignites the canopy in that way. So knowing explicitly where these shrubs are in relation to a canopy is incredibly important for predicting things like canopy fires. And then again, with what I was calling thick fuels or coarse woody debris, knowing where these are with respect to things like a canopy can be really important because since these logs release energy over such a long time, you can end up with a really long and a large amount of energy being deposited into the canopy. So you may not necessarily start a canopy fire, but these trees can be susceptible to being heated up for long periods of time, and you can actually cause tree mortality in those cases. So even knowing where you have a lot of downed woody material can be very important in terms of predicting what the impact is going to be on the forest, given the fire spread through it. And last but not least, the fuels leg of this, continuing on. But these fuels are a mosaic of all sorts of different species, from the surface fuels to the species of trees to also whether they're live or dead or stressed. Them being stressed can tell you something about what their actual moisture is. They could be standing dead, which makes them really good timber for a fire to envelop and really burn intensely. But then also there's kind of an idea of continuity of these fuels. So whether you're talking about the continuity of the canopy and how connected it is, can really change how a fire is going to behave. And even with the surface fuels, whether you have very patchy grass or just a full carpeted grass, this can have really significant impacts on how fast a fire can spread, but also given different moisture conditions, how easily it can spread through those fuels. And then kind of my fourth added leg to the triangle or square is moisture. And so we even if you explicitly place all these fuels and you have a really good approximation for where they're located, it's also really important to have a good idea about what the moisture content of these fuels are. Because if they're soaking wet, no fire's going to happen. And so kind of some things that can play into that are things like evaporation due to sunlight. And so ultimately, knowing where trees are tells you where shading is, which tells you where you can have higher moisture contents. And so in this case, add the sun out, you can see underneath the tree there's more moisture, and going out there's less. But on a cloudy day, you may have much higher moisture contents across all of these areas. And then also, if it rained in the past few days, this can also have significant impact on fuel moisture contents and whether or not a fire is going to carry. So that's just another aspect with fuels, their locations, shade from canopy, also driving moisture, which can have significant effects on whether or not a fire is going to carry and how intense it will be. All that being said, even if you have the best model, if you have bad inputs, you're going to have bad predictive capabilities. So really, one of the most important things for any of these models is that we have really strong, reliable, and useful inputs for them. So this goes into where we're placing 3D fuels, how they're described in terms of moisture and their loadings and the total mass there, and then going on into weather and things like that. But yeah, that pretty much covers fire and 3D fuel inputs.
Amazing. Thank you so much for your time. I also want to thank you for putting the red X over the top of the hand above the candle. I know that scientists are not always loaded with common sense or
PSA.
yeah, exactly. So a little do not try this at home warning seemed
Yes.
appropriate. I got to say, every one of these talks, I learned some really interesting stuff. For example, I didn't know that you have to boil water out of wood in order for it to get hot enough for the chemical transformation or reaction to happen for it to sustain fire like that. I see it in campfires, right? Like it boils
Mhm.
out of the wood if you've got wet wood and a hot enough fire. But I didn't realize and the idea that that's a heat sink too, that could then stop the fire simply because it runs out of energy um, to create more fire was interesting.
Yeah,
I
and
also thought
even
it
if
would,
you, oh, sorry.
no, go
Uh,
ahead.
like in like lab experiments, if they when they have thermocouples like within like a log of wood that they're heating up, you can actually see the temperature raise up and then it sits at boiling temperature for a while that moisture gets boiled off, and then you see the combustion start and the temperature ramps up again. So there's like a shelf that happens.
That's really interesting. I have a pressure cooker that I use at home sometimes. And of course, the joy of that is you can get water to a higher temperature. Or is that right? Because it's under pressure, it
Hmm.
can reach a higher
Yeah, steam
temperature
can go
before it
much
boils. Yeah. So it fits with other little things that which is great. The other thing I thought was so fascinating is it sounds like understanding where your trees are, how big they are, probably even what species they are, has impacts on a variety of different inputs. That's not just your fuel. That's how your wind works. That's where you're likely to find more and less moisture. So you have um, echoing effects around your model from getting your vegetation models right as an input to begin with.
hmm Yeah, everything is coupled from the weather. I mean, even weather can affect your moisture in terms of how much airflow is passing over those trees, because that will tend to dry them out. So, yeah, everything's coupled.
Yeah. Another interesting thing that I wanted to point out or reflect on too is that when we talk about prescribed burns, a lot of times the goal is to burn off a lot of surface fuels, fine fuels, I think you called them thin, and leave the canopies intact. And your fuel structure on the ground, figuring out where these trees and shrubs are and how thick they are and how likely they are to expose the canopy to heat and therefore mortality, tells it's not just about how much you burn, but the effects of the fire sort of after you might think it be out, whether or not you're actually going to meet your goals in these burns.
Yeah, absolutely. And like I was saying, those logs and things can really do a lot of damage in terms of exposing the canopy to much higher heat doses. And yeah, it's about knowing where those things are and whether your fire propagating through those thin fuels was hot enough to substantially ignite those thicker fuels.
Wow. Well, again, I want to thank you for taking the time to talk to us this afternoon. I think that this lecture slots in really nicely with what we heard from some of our practitioners and is going to provide a great bridge as we start to talk about how we gather data about vegetation that we use to create the models that are the inputs for these sorts of broader models like QUIC-Fire that run underneath the Burn Pro platform. So thanks again, David.
Awesome. Thank you.